Hopefully you took a little linear equations quiz yesterday. Hopefully it went okay. Did anybody have any specific questions or concerns about that quiz or anything that was contained on it? It was pretty straightforward, hopefully. It wasn't meant to be tough. Just kind of a quick overview or reminder of linear equations. So the reason we were doing that, though, is because I was showing you yesterday that we use linear equations and statistics as a way to do inference. You can have nonlinear equations, too. It can get a lot more complicated than this. We just do linear equations in this class just to kind of show you how it works. But basically the idea is that, if you look at variables and you find that those two variables have some amount of correlation, in other words, there's a pattern between how one behaves as the other changes, then it makes a lot of sense that you could fit some type of function, to describe that relationship, and then you could use that function to make predictions about what's happening on one variable based on the other. All right. Okay, so then that's the goal, right? It's like we're going to use one variable to predict the other. We talked about some examples about why that could be useful, which was it was almost foreshadowing because I was talking about wrecking my car, and then my wife wrecked my car last night. So.
No.
I know. Nobody was hurt. That was the good thing. But anyways, I just thought that was really unfortunate. I was like, man, we were just talking about me wrecking my cars today. I should not have been talking about that. Yeah.
Is it total damage?
No, I don't think they're going to total it. It's a newer car. It wasn't like ridiculous. It's just some teenager just turned in front of her, and he'd only been driving for a couple months. Kind of felt bad for the guy because he didn't get a ticket though, so that's good for him. So, anyways, it was all good. But anyways, so the point though is so the idea is you got a data set that has a linear pattern. You can check that looking at the correlation coefficient because that gives you a judgment of how strong it is. Yeah.
Yesterday when you used that Excel
Yeah.
page,
Yeah.
that was to identify the correlation.
That's part of it. Yeah, that is part of it.
Besides that Excel worksheet, how are we supposed to identify them?
Well, you would have to use some type of software. There's a formula for it, but I don't expect you to calculate it by hand. On an exam, I would not give you data and expect you to calculate that number. I would either provide that number, or you could reasonably estimate it by looking at the scatter plot. So actually, since you mentioned that, I am going to pull that up because I'm going to need it. So that was here in the calculator. Let me just download it, pull it up again, and then go back here. But I'll show you, if you look at I'll show you the quiz, for example. And then you can also look at the practice test for the next test. You'll see some examples where I put it on there. But, I will give you, I might ask you to, predict. You could look at a scatter plot and give me a rough estimate of what the correlation coefficient could be. But I'll also provide, if I want you to know what the correlation coefficient is, I'll provide the output in the format that the spreadsheet reports it. And so mostly what I'm interested in here is just interpreting and applying the regression, not necessarily actually constructing the correlation coefficient or the line, because nobody actually does that. I would never do that in real life. I would just put my data into a software, and I'd have the software produce the correlation coefficient and the line for me. But then interpreting it and using it, that's kind of the important part. So you can see here, I give you a lot of output, and I just expect you to interpret it, more or less. Okay, I'm not actually expecting you to calculate the values. So I kind of explained yesterday how the line gets calculated. It gets calculated using a process called least squares regression. Essentially, we're trying to predict, and so anytime you make predictions, you're going to make an error. Yeah.
Just making sure. Are you recording?
Yes. Yeah, I did it. I think. Pretty sure. I'll check. But the idea here is, we're trying to minimize our errors, and so we minimize the sum of squared errors. That's why it's called least squares, because you're finding the line that produces the least squared errors. And I'll check. Yeah, looks like we're good. Okay, that's where we left off. So I produced it. So the data, the Excel spreadsheet is already preloaded with data. It just happens to be preloaded with the car data because I used that one. So here it is. So all your X values, the weights go in here, the Y values go in there. The order matters because they're tied to each other, right? Because that weight is tied to that fuel efficiency. You can't just like put them in any order you want. That's going to cause weird things to happen. So it matters. But you put them in there together, as a pair. And then I produce the plot, and then this is the output. So yesterday I talked about the correlation coefficient. But typically when you run a linear regression, if you use a software program that does it, it's also going to just automatically generate some other stuff. Like one thing it'll generate is something called the coefficient of determination. That's not that important for our class. It's literally just the correlation squared. It's kind of like when I talk to you about standard deviation versus variance. The coefficient of determination matters for some things, but not anything we're going to do. But a lot of output will generate it. And then usually it'll generate the intercept, the slope, and then a lot of times it'll produce the equation itself. And so here you can see what this line tells us. It says that if you want to predict the fuel efficiency of a vehicle in this class, because they were all domestic sedans, I think, or domestic cars, I don't know. If you want to predict the fuel efficiency of something in that class, then what you could do is you say, if you tell me how much it weighs, I can plug that weight into this equation, and then you just simplify it, and then the line will actually give you a prediction of the fuel efficiency for that vehicle. All right, and it's kind of, the way I have it formatted is kind of weird, just because you see plus and minus, but it's a negative slope. If you were going to actually write that down, we would actually do that. The line would actually be, let me put it here, smaller. It would be, so I told you yesterday we use the y hat notation. The hat just means it's going to be a prediction. It's not an actual value. And so the slope was, the intercept was 37, we'll round, say 37.36, and then minus 0.0047 x, right? And so what this is telling us is that you can predict the MPGs based on the weight of the vehicle. That's the idea, right? So right here, you have a situation we can say, okay, so if you come to me and you are presenting a 4,200 pound car, we can pretty easily predict the fuel efficiency of that car using the line that the software produced. You just plug it in, right? So you just say, okay, well, 37.36 minus 0.0047 times 4,200, right? 17.62. Anybody else get that? 17.62. Somebody else want to try it just to confirm? I trust you. I just like to get it. Anybody? Confirm? Didn't dispute?
1762.
Cool. Okay. Yeah. And now the prediction is just that, though. And what it's a prediction about what's going to happen on average, basically. So what it's telling us is it's saying that on average, a 4,200 pound car, these are all, they have to be in this class, though, right? It would have to be something equivalent, like a 2015 domestic car. You couldn't try to predict this for a truck or something made in 2020. It wouldn't be appropriate. But on average, a 4,200 pound car from that class would get 17.62 miles per gallon. Obviously no single car is probably going to get exactly that fuel efficiency. But the cars in that class on average should get something around that. All right, that's the idea. Okay. Now, what happens, what if you tried to plug a 6,000 pound car into this equation? It's going to, you're going to get your fuel efficiency. You could do, there's no reason you can't do it. Right? There's no reason you can't calculate, I meant to put my number in there. What does it come out to be if you do that? Yeah, and so if you plug in 4,200 there, you get like 9.16 miles per gallon. Now the question is, does that number mean anything, or is it useful information?
This is useful.
Do you think so?
Wait, I don't think
What's the
there's.
question?
Well, is that number meaningful? Like, do you think that this is appropriate? Do you think that this is an appropriate use of our line to try to make a prediction on a 6,000 pound car? That's my question.
No.
Seems kind of like an outlier.
Yeah, 6,000 is way out. You said no, why?
Well, I mean, most of the cars are in that range, and so if it's a 6,000 pound car, it's probably not going to be in the same category as the other.
Yeah, first off, I'm suspicious that this is even the same kind of car. But also, it's an outlier. I don't see anything on there. Also, I don't even know if there are cars that get 9.16 miles per gallon anymore. Do they exist?
Maybe like a really crappy tread.
But a new car, like a one built, are there any new cars that get 9 miles per gallon?
Yeah.
Do they exist?
Only if you're a wide open problem. But
Oh, well, yeah, maybe like something really weird, like a really, yeah, I don't know. There's not many, right? Yeah. Which, oh, yeah, sorry, yeah. That should have, yeah, good call. Yeah, that should be 6,000. But I'm assuming you calculate, whoever gave me that number, I'm assuming calculated with 6,000 in it. Yeah, you guys are better than me, so. But yeah, the point is that you have this set of observed data, and the predictions are going to work reasonably well as long as you're making predictions within that range. But you have to be really cautious if you're going to try to make predictions outside that range, because there's a good chance that that relationship may not hold outside of that range. Because like if you think about what happened, this is called extrapolation, which I'm going to define in a second. But if you think about on my graph, actually my Excel file not doing what I want it to do is actually almost a blessing, because what it shows you is where is all of our data. All of our data is in sort of this narrow window of possibilities. It's kind of right here between 3,000, whatever, and so there's a strong relationship there, but I don't know what happens outside of that range. I have no idea, right? And so I don't want to make predictions about a 6,000 pound car, because honestly, I don't know if this pattern continues or not. It might just flatten out, or it might take a nosedive or something like that. And so you don't want to make predictions for data points that are outside the range of what you observe. If you do, I don't even need that picture anymore. It's called extrapolation. So I'll just erase that, actually.
I think it's funny how in the y-intercept, it's like the car weighs 0 pounds, it would get 37 miles.
Yeah, actually, we'll talk about that in a second, because it may not even make sense to interpret that intercept at all. But extrapolation. Oh, what the heck's going on, man? Come on, you can do it. Eraser mode. How about pen mode? Extrapolation occurs when attempting to make predictions outside the range of observed data. And it's bad. It's not good. You shouldn't do it, basically, is the point. And so, like I said, if you look at I might as well draw it because I can't erase it. But we had this sort of narrow window of data where we saw this relationship, and the line worked reasonably well to describe it in that range. But in reality, I don't really know what's going on out here because I never saw it, right? And like you said, I mean, the line, you could throw any number in there. Like you could throw 0 in there. What's the fuel efficiency of a 0 pound car? I mean, the function will return an answer. Yeah, the function will give you an answer. It just doesn't mean anything, because the function is just a mathematical way to describe that relationship, but it's not necessarily meaningful outside of that range. You know, eventually, if you got a heavy enough car, if you started plugging in if you plug in like 20,000 pounds or something, it's probably going to tell you that you get a negative fuel efficiency. That also doesn't make any sense. You know, so you got to make sure that you're doing predictions within the range of the data set. And this also, and really I should put, you know, or it could also be like observations, which come from a different population. You know, so I shouldn't use this line to try to predict the fuel efficiency of a truck or a motorcycle, right? It's not appropriate. Those are different populations. So it works really well. I mean, so it's powerful in the sense that you can make predictions of one variable off of the other, but there's also limitations in the sense that you can only really do it within the range that you observed your data, and you really can't apply that to anything outside of the population that you're observing. So, yeah? Okay. So the point is it can happen as bad. You just shouldn't do it. Okay. You mentioned the slope. You mentioned the intercept, and so the thing is when in a line, right? And this is kind of what you took a quiz about. I talked a little bit about slope and intercept in that quiz. The slope actually always has a really nice interpretation, but the intercept might mean nothing. It's possible. So like if you take our example. So, like, it was y hat equals, I don't even remember what was the number?
37 point something.
37 point, like, I rounded it, 3.6? Yeah, 3.6 minus 0.0047 x. Now, what is it? Is this the slope or the intercept?
Intercept.
Yeah, so in statistics, we typically write the intercept first, and then right here is the slope. The slope is always meaningful. Right? So what does it mean? What is that slope telling us?
Drops. At what rate?
At what rate what drops?
The fuel efficiency.
Yeah,
Economy.
the fuel efficiency, it tells us the rate the fuel efficiency drops as what happens? Exactly. So what it tells us, the slope is telling us what's going on with the y variable as the x variable changes. And so the way you would interpret that is you could say something like, for every 1 pound increase, so for every 1 pound increase in weight, because that's the x variable, that's what it gets multiplied by. So for every 1 pound increase in weight, what do we predict? We predict a 0.0047 decrease in miles per gallon fuel efficiency. Okay. So one of the things I'll ask you to do on the quiz or the exam is I might provide the line for you and ask you to make predictions, but I may also ask you to interpret the slope of that regression line. What are we actually saying? Okay. And it's a decrease because it's negative. You know, if you had an increase, you'd see a positive relationship. All right. Okay. And then now the intercept, though, the intercept may not have. You can interpret it. It might just be sort of gibberish or something. Because what is the intercept telling you?
Where it intercepts y.
Yeah, it's where it intercepts the y-axis, and that happens when x is what?
0.
0. And so what it's saying is it's saying that for a car with what? With weight 0, we would predict a fuel efficiency, like MPG fuel efficiency of, 37. But it doesn't make any sense. Efficiency. Yeah. Right. It's kind of doesn't make sense. But why doesn't it make any sense?
Because there's no car.
Because, well, first off, you can't have a 0 pound car. That's the first problem. But also, even if it theoretically existed, what would using this line to try to predict it would be what?
Completely irrational.
Yeah, it's what we just talked about, right? 0 is extrapolation, right? And so 0 is not even an appropriate value to plug into this equation. So the intercept might have an intuitive interpretation if your data set includes zeros or negative number. You know, if your data is near 0, that might make sense. You know, but you know, if you're talking about if your x variable is like number of hours per week a student works. Well, there are a lot of students who work 0 hours per week, so 0 might make sense, and the intercept might make sense. But if your data is nowhere near 0, then the intercept's never really going to make a lot of sense. It's just like a remnant of the fact that the line goes forever in both directions. Eventually, it's going to cross the y-axis. It might just not be anywhere that makes sense. So, does that make? Okay. But the slope always means something. Okay. All right. So I pulled out some other data, and this is a change in the slides. I just added this in because last time people felt like they wanted another example. So this is an example with another set of data points. And so what it was is it was just randomly selected students to look like absences versus their GPA. And so if you have a new data set that you want to work with, then you can just reload the data here. So I'm just going to take our data. So let's say you wanted to predict someone's GPA based on the number of absences. Maybe you think that's a reasonable thing to do. Maybe. You at least could see if there's any pattern. By the way, I don't know how this is going to turn out because I haven't done it yet. So as our x values, I could change this out and swap it for the absences. Okay, and then over here, I could put the corresponding GPAs. Okay, and then my function here is going to automatically update. So actually, what can you see here? What does it look like? Happens? Yeah, there is some correlation. It's not as strong. It's not as strong as the relationship between the weights of vehicles. But now in this situation, is a 0 a reasonable input for the x value? It is. So the intercept might actually mean something here. You know, it might actually be intuitive. It's a relatively strong correlation. So negative 0.7. That's pretty good. Yeah, that's pretty good. Anything around 0.6, 0.7, you're getting into territory where you're talking about pretty strong linear relationship. So there's definitely a linear relationship here, and then the computer here just kind of spit out the actual relationship. So it says that if you want to predict someone's GPA based on absences, a reasonable way to do that is go 3.7637 and then subtract 0.1455 times whatever their number of absences is. That's the deal. Okay, so I'm going to pull that onto here. So I wonder if it'll copy just the values. Let's see. It probably won't do. It's going to get really mad at me. Maybe if I do a paste special. Let's see if I can do it. Perfect. And it was a minus. All right. So that's the line. I'm going to. Okay. So it looks like. And what's the general relationship here?
Absences to GPA.
Yeah, and the negative slope right here, it shows us that in general, it looks like as absences go up, then the GPA in general is going down. Now, this is just a trend on average because if you go back and you look at the plot, obviously that doesn't necessarily hold true for everyone, right? Because you have the trends in general, but there was a person with 12 absences that had a higher GPA than people with less absences and so on. Right? It's not a perfect relationship. Regressions just attempt to make predictions on average. That's the point. Just looking at overall trends. So if we take that line, then we could do an interpretation of the slope and the intercept. I actually should have copy-pasted that on the next slide. That's what I should have done. I'm going to take that again. Let's go here. Real quick, I'm just going to put it here too. Boom. All right. Okay. So how would you interpret, say, the slope here? What is that telling us?
Okay, missing those 0 days, then it's
That would be the intercept.
Oh, the intercept, right.
Yeah. But the slope is this value right here, so it should contain this number in it somehow. So what does the slope tell us?
For every day X that a student misses, their GPA will drop.
So for every additional absence, what do? We predict a decrease in GPA of 0.1445. That's the general trend. And of course, this is on average. On average. That's supposed to say average, but you get the point. Okay. Now, what does the intercept tell us?
What I said.
What you said. That's right. The intercept tells us that if you had a student with what? Yeah, so for a student with 0, oh, that's interesting, absences, and it disappeared. What do we predict?
GPA of 3.76.
Yeah. Of 3.7637. And again,
On average.
this is on average. So, okay? Now, in this case, that makes sense. Because can you have 0 absences? You could. And if you looked at the plot, does it look like those students would, on average, probably get a GPA around that? Sure. Okay. So, the intercept can make sense. Yeah? Everybody feel like they could interpret a slope and intercept of a regression line?
So interpret just straight up means just explain it.
Yeah. Just explain it. Tell me what it means. Don't just give me the number, but tell me what the number actually means. Even if it's nonsensical, it's possible. Yeah.
So if your slope's negative, is the correlation also going to be negative too?
Yes.
Positive, positive.
Exactly. Yeah. So I had 2 examples of a negative correlation, but you could have positive correlation. I think the one on your quiz is a positive correlation because it has to do with like sunlight and crop yield. So, all right. Then once you've, as long as the regression, the correlation coefficient is like pretty decent, then it makes sense to do predictions. So if you have a student with 9 absences, what would you predict their GPA will be? You just plug in 9, and then what does that come out to be?
I think I did it wrong.
2.46?
Yep, 2.46.
Yeah, we'll round, but yeah. Right, so you'd predict them to have about 2.5, 2.4, somewhere in that range, GPA. And you could look at the plot and kind of eyeball it and kind of realize that that's probably where it is. But if I'm asking you to do the prediction, I'm not asking you to eyeball it. I'm saying use the function. And the reason that we use the function is because a computer can compute this in like a nanosecond, and so a computer can do massive amounts of predictions all at once if you have functions built in. You don't really want to eyeball it. So. Yeah? Okay. Everybody feel pretty comfortable with that? So then if you ever see any studies where they're talking about correlation, what they're talking about is they're talking about the correlation coefficient. And what they did is they ran a regression and they looked at whether there was a pattern between the 2 variables. You have to be careful about correlation versus causation, which we talked about yesterday. This one, you may be able to make a causal argument. Maybe. Yeah.
Will we always get the y-intercept?
Yeah. I'll provide that output for you. Yeah. Mm-hmm.
But you won't give us like the R.
But I may, I think I have a question on there. Or like, I think it's maybe on the practice test or something. Like if I give you a scatter plot, you should be able to look at that scatter plot and you should be able to give me a reasonable estimate of what that correlation coefficient would be. We know what it is now, but if I just flash the plot onto a page and said, hey, guess what the correlation coefficient right here is? I don't need an exact answer. If you told me negative 0.5, negative 0.6, negative 0.7, I would say, yeah, it seems reasonable. You don't have to get it right, but don't tell me it's positive 1. Don't tell me it's 0. Don't tell me it's negative 1 because it's not.
And prediction is just double that.
And what?
And prediction is just squared. So,
No, that's the coefficient of determination.
oh, yeah.
That value can be used in some tests, like if you're trying to test whether or not a variable is significant. It's a long story. It's not that important.
Okay.
I really just shouldn't even include it on there, but it exists. Just forget about it.
Okay.
Yeah. we'll just boop, gone. Don't worry about it.
I like it.
It's not that important. Okay. All right. So everybody feel okay about that? Okay. So that's what your next quiz is all about. It's all about, and you saw, I kind of previewed it, but it showed some scatter plots, asked a bunch of questions, asked you to interpret slopes and intercepts, do some predictions, things like that. All right. You can compare two non-quantitative variables. It is possible. So all of this, notice, is all about quantitative, quantitative, absence is quantitative, GPA quantitative. One happens to be discrete, one happens to be continuous. It's not that important. You can still run the regression as long as they're both quantitative. You can't really do the same thing if you're comparing qualitative variables. And so one of the main ways that we're going to do it in this class, and these will continue to pop up in the next module as well, is we can use contingency tables. This is an example of a contingency table. And a contingency table helps show us how two different qualitative variables compare to each other. So you'll notice this is comparing two things. One is employment status. The other is level of education. So there's two variables here. They're both qualitative. And then inside, we have a whole bunch of numbers. Right? Now, there's some terminology we use here. So like inside here, those numbers in there, those numbers describe two things happening at once. Right? This number right here describes what? People that are unemployed and did not finish high school, right? It's saying two things. So on the inside, these are called joint events or joint numbers, joint values, all right? Because it's talking about two things happening jointly or two things happening together, all right? And then out here, what about these numbers out here? Except for the total. The total's not really. But do they talk about two things or what?
Just one thing.
They're only describing one thing. So these numbers out here, they only describe one event, right? So like 61,442, that just describes the number of people which are high school graduates. Well, right, one thing. And so these out here, these are what we call a marginal. Well, they're in the margins, that's why. Okay. And the reason they're called contingency tables is that when you start working through these, you can start to look at how one variable behaves contingent on what's happening with the other. So if you were to look at, say, this table, I think I want to copy this table and go one more slide with it because I messed it up so bad. Let's go. Paste that bad boy. So I'm going to bring it over here. Let's say we want to just start looking at some values associated with this table. Like, what types of questions might you be able to answer or explore with this contingency table?
Your employment versus your degree.
Yeah, you could look at, okay, how do people's employment status, how is it affected by their level of education? What do employment status look like contingent on people's level of education? All right, so what you could do is we could convert these. Now, the raw numbers don't do a very good job of describing this. Because the fact that there's way more high school graduates employed than did not finish high school graduates employed, is that significant that the number is way bigger? That in itself is not that significant because, there's 33,000 people here and 10,000 people there, but that might not actually really mean very much. Why?
Ratio.
Yeah, it's possible there's just way more of these types of people than those types of people, which is true. So in the U.S., there's way more high school graduates than there are non-high school graduates. That's just true. Okay. So what's a better way to compare these numbers? What could we do to these numbers to help us compare?
Create ratios out of them.
Yeah, turn them into like proportions or percentages, right? Because like relative frequency, we talked about that before. We can convert our raw counts into proportions. And that's a better way to look at it, because this 10,000, it's not really comparable to 33,000 because the numbers are not the same at all, the totals. So what we could do here, though, is we could convert these into proportions. So like, for example, for the did not finish high school status, if I wanted to convert this into proportion, then how would I do that?
Divide employed by the
Yeah, take 10,179 divided by 24.395. So do that for me. And what do you get? And let's just round it to like 2 decimal places. 10,179 out of 24,395.
0.41 or 0.42.
0.42 if you round? Okay, so then it goes 0.42. What about the next one? 945 out of 24,395. I'm going to do this for all of them, by the way, but so you can get ahead of me if you want. But do 945. So this is going to be 0.04. Yeah, so the next one's got to be something like 0.54 is my guess.
It's 5 more, yeah.
Yeah. So I'm just converting all of these values into proportions, okay? But these proportions right here, this is within, no high school. So it's like among people with no high school, contingent on them not having a high school degree, 42% were employed, 4% were unemployed, 54% were out of the workforce, okay? And then we could do the same thing for high school graduates. What do those numbers come out to be? So 30,
5%.
what is it?
55.
0.55?
Yeah.
What was the next one? We're doing 2012. It's about the same, 04, 03 or something. I can't remember. What did it come out to be? 0.03 if you round. Okay, so then the other one's got to come out to like 0.42?
Yep.
Yeah, okay. And then, how about that one? So among people with some college degrees, what's the employment rate?
0.65.
6.5?
Yeah.
Okay, and then what about the unemployment rate?
0.03.
Also 0.03. So then this makes this, what, 3.2?
Yeah.
Okay, and then what about this? So for employment among people with bachelor's degrees, what's that?
0.72.
7.2, and then the unemployment is
0.24.
0.24 or 2.4?
2.4.
The unemployment rate is 24%?
0.24. Yeah.
I'll do it.
Okay. Yeah, we did it.
I don't think the unemployment rate among college grads is 24%.
0.02.
Oh, yeah, I think it's 0.2. I think I don't know what happened, but and then so that means this has got to be some 26 or something, probably, ish. Okay. So what happens? What do you notice?
What were we doing the last one?
Yeah, you're 0.25 or 0.26 or something like that. Yeah.
The unemployed percentage decreases as they gain more schooling.
The unemployment rate moves, but how much? Not actually that much. So the unemployment, it definitely goes down. Now this data must be taken from a year, a pretty decent economic year, because unemployment rates at 4%. That's pretty good. The national average now is somewhere in the 3% or something, I think. It's pretty low, so that's pretty good. But then the big shifts happen where? Employment rate and the out of the workforce rate.
What is out of the workforce?
What does out of the workforce mean?
Stay home.
Yeah, you could be out of the workforce for a lot of reasons. Unemployed is really specific. Unemployed means, anybody know what unemployed means?
Looking for a job and not.
Yeah, it means that you're actively looking for a job, but you can't get one. Right? So you're applying for jobs, you're out there trying to get jobs, but you can't get one. That's why the unemployment rate is so low, even though obviously way more than 4% of people are not working. Okay? But those people get classified as out of the workforce. So how do you get classified as out of the workforce? There's a lot of ways. Like you mentioned, you could be a stay-at-home parent. You're out of the workforce because you're not looking for a job if you choose not to work. What else? You could be disabled. You're out of the workforce. You could be retired. You're out of the workforce.
You can be a kid.
You could be a child. Yeah, I think these are adults. But yes, you could be a child and you're out of the workforce. Most people, a decent chunk of Americans are not in the workforce for those reasons, a decent proportion. All right? And so what you see, though, is you see the employment rate goes up while the out of the workforce goes down. So it's almost like as the education level goes up, you're seeing people shift from here to here. You're not seeing as much movement in the unemployment rate, which is interesting because some people might suspect that that would move more. It turns out that in really good economies, the unemployment rates are very close, but in bad economies, that number widens. So if you look at a graph of bad economies versus an unemployment rate, the bachelor's degree unemployment rate typically hovers between 2 to 3%, but this, the no high school, that typically can vary from like 4% up to like 9% in bad economies.
Is it just because there's such an influx of?
I think it's because in a bad economy, if you're more susceptible to a bad economy if you don't have a higher level education, because those are the types of positions that tend to suffer more, which is true. And so there's way more variability. So, but there's not a huge difference. Now, why do you? Now the question is, there's obviously a correlation because you can see the pattern. It's not necessarily linear, and we can't like plot these on a graph, but there's correlation between these two things. The question is, do you think it's causation, or do you think it's just correlation? Because you have to ask that question when you look at comparing two variables. Some say causation, some say correlation. Why do you think it's causal?
Because you're changing what degree or how much schooling they have. That's what's
Okay.
actively changing, and then in response, you're getting a different level of employment.
And do you think it's the fact that they went to school that made them more likely to be employed versus not in the workforce?
Yes.
You think it's causal?
I think it's because it's like it could be like considered a controlled variable, like where if someone did not finish high school versus someone who has a bachelor's degree, it's like a clear definition of the numbers are completely different.
They are very different. I'm not denying that. There's like a really high correlation between these two. My question, though, is does that mean that the education is what's causing people to be employed at a higher rate or to be out of the workforce at a lower rate?
I think the people that go with the bachelor's, whatever, they're purposely going to whatever field they want to. So that's
See, that's the thing. Why do people get bachelor's degrees
because they want to go
anymore, right? Why does anybody get a bachelor's degree? Why are you guys here? Are you guys here for the love of statistics? How many of you guys are here because you just love school and you just want to get educated and you're just getting a general education? Some people, there are people, right, that just go to college because they want to learn more and whatever, right? How many of you guys are here because you have a career in mind or you're trying to get a specific type of job? Okay? A lot of people are there in college for that reason. So it's like, well, who are those people that got bachelor's degrees? Why did they get bachelor's degrees? Because what? Because they wanted to work or they had to. I mean, who wants to work, right? If I didn't have to work, I wouldn't be here. I love my job, but I'm not going to do it, right? If I had tons of money, all right? But it's like, so part of it could actually be that. It actually could be the inverse. It almost like could be inverse causation. Almost like seeking the degree causes the, you are already this person that wanted to be employed. You already were in this group, And then what about not in the workforce? Why do you think? How come like this is so high for not in the workforce? Do you think it's because they have a lower level of education, or do you
they
think
have less options? They
Less
just choose not to.
desirable.
Could be. Could be, but think about the people that are out of the workforce. Like, what's a huge chunk of people that are not in the workforce?
Moms.
So it could be like stay-at-home parents. That's one of them. I don't know. Do you think that stay-at-home parents are more likely to have not finished high school for some reason?
13 parents.
Well, it could be. Yeah, I mean, it could be a situation where they had kids early and they didn't finish high school. I'm thinking of a different chunk of the not in the labor force that might really mess with these numbers, though.
Retired.
Yeah, I'm thinking of retirees. A huge chunk of that not in the labor force. What percentage of Americans are retired? I don't know, a lot. 15, 20%. But when did they go to high school? Hold that thought real quick. I'll get back to you, Gina.
A long time ago.
Yeah, the people who are retired now, they would have been graduating from high school like, 50 years ago? 1950, 1960? Well, what was true 50 years ago?
Or no.
It is
That was a little more than
Yeah,
50.
yeah.
That was like 100.
But graduated as much.
Yeah, I mean, it's just a high school degree wasn't as big of a deal 50 years ago. In 1950, a lot of people didn't graduate high school, right? And so part of this number is just being skewed by the population itself. There's a bunch of retirees in this group right here, you know, and retirees are a bunch of these, and they happen to have high school degrees at a much lower rate. Okay, so a lot of these people right here might have actually worked their whole life, you know, without a high school degree, and now they're retired, but they're getting lumped in this category and making it look like it's the fact that they didn't go to high school is why they're out of the workforce, and that's not it at all. They're just retired, or something like that. Yeah. Do you know what you're saying?
Is there also a portion like for homeless?
I don't know. That's a small portion of the population, so I don't know how much of an effect it would have at this level. But you're thinking, I don't know.
Like
I don't know.
At least like the college part,
Yeah,
not like for the high school part, more like the college part.
I don't know. I think my guess that's such a small chunk of the population that I think it would be hard to see their effect on a broad scale, just because it's a very small percentage. But I don't know. Anyways, but you get the idea. The point is, it's not so clear cut. It seems at the outset that it's a causal thing, but it's actually possible that it could actually be not. It could actually be much more correlation than we think. You know, because people tend to intentionally go to school because they want to work or because they have to. So, anyways, this is actually looking at probabilities like this. I have one more example I'm going to show you. This is a lawsuit. This was like a gender bias lawsuit against UC Berkeley, and what happened was it was a female student who applied for graduate school at UC Berkeley. She was denied entrance, and she felt like she was discriminated. She felt like women were discriminated against in the admissions process for graduate school at UC Berkeley. That was the gist of the lawsuit. And if you look at the overall numbers, it actually looks like she has a pretty good case. So if you look at this, what does it look like?
There's more men being accepted.
Well, first off, if you look at raw numbers, there's like way more men accepted than women. Of course, if you look at the totals,
30% of women get accepted. Well,
yeah, the percentage doesn't look good because if you convert these into percentages, right, among men, how many men were accepted, right? 1191 out of 2590, what is that? What does that come out to be? 40-something? 50? I don't know. 1191 over 2590?
I didn't.
That'd be lower, yeah. 0.46.
Yeah, like 0.46, which means this number. Well, I don't really care that much about the not accepted. It's just it's just 1 minus that. But and then what about women though? Women
0.3.
0.30 if you round.
Yeah.
Yeah. So you know, you got men at a 46% acceptance rate, and you got women being accepted at a 30% acceptance rate, and so that's kind of troublesome because that looks pretty bad. And these were applications for graduate school, and in graduate school, you know, you can assume that these two populations were similarly qualified. Probably, there's a good chance they were both similarly qualified. But in graduate school, well, what do you think? So what types of things might you ask before you just go ahead and decide? Okay, it looks like there's a problem here.
What were their GPAs?
Yeah, well, let's assume they were all equally qualified because I think they were. Let's say the men and the women were all equally qualified for what they were applying for.
It's all in the same time frame that they applied, right?
Yeah, it's all within 1 year. It was all the same year, and they were applying.
Like what they're going to grad school for?
Yeah, so that's what the college, they say, okay, so this looks pretty bad, but one thing you may want to consider is okay, well, where were these men and women applying? Like what programs were they applying for? Okay, and so that's what they did. And so I broke it apart here, and so here's the breakdown. So they basically had, so typically if you're going to graduate school, they're broken into like colleges. So there's like the College of like Arts and maybe something in there. Then there's a College of Engineering, and there's a College of the Humanities or something. There's different programs basically, and you apply to a specific program. And so here you go. So this is what it looked like. So they split it apart by program. So they broke them into basically 6 different colleges or 6 different fields, and then they looked at the acceptance rates and the denial rates among men and women. So, what do you notice?
Men apply a lot more than women.
There's a lot more men than women in general, but we already knew that from the totals.
There's different like programs that one sex would apply for compared to the other.
Yeah.
Yeah.
But
So if you look right, so if you look at the breakdown, like look at program A. This program is like all men. I mean, it's not all men, but it's a lot of men, not so many women. And then program B, tons of men, not that many women. What happens as you move down the scale, though? Like for example, here,
More women.
this is much more women, right? And this one's slightly also more female, higher percentage of female. Yeah, some of these are C is also female dominated. This one's pretty even across the two. So what do you think? What do you also notice though?
There's split pretty even.
It's interesting because like 80% in group A of the women were accepted.
Yeah, this one right here actually, women had a very good chance of being accepted in this program. It was like you said, like about 80% of women got accepted into this program. You could calculate the men's acceptance rate there. It's actually not as high.
It was 0.6.
Yeah. So actually, percentages are good. So the raw counts matter because it shows us that men and women are distributed not uniformly across these programs. But then if you look at the acceptance rates, so like you just calculated that one, you can look at the acceptance rates. What happens across the programs?
Pretty even. Some of them.
Yeah, if you go across the program by program, go program by program, which program is discriminating against women, if any? You can maybe argue C, but even that's within a couple percentage points. That's pretty easy to explain just by chance.
It looks like F is really like an output, but you know, version of the high.
Yeah, it's like you can. There's really no evidence that any specific program is discriminating. It doesn't appear like it, right? It doesn't seem like it. And so the question is, how can every single program not discriminate, and yet at the overall level, it looks like women are discriminated against?
Oh, so I noticed that in the groups that had like a larger amount, so for like the A, there were way more men applying for that one.
Yeah, remember where the men were. Yeah, all the men were piled up over here, right? Well, what's true about the acceptance rates in those programs?
They got way higher.
Yeah, the men were all applying to programs that are easier to get into. And then where were the female dominated? It was like C, E, and F were the ones that were more female dominated. But look at their acceptance rates. You know, this is half of those two, and then these are even worse. Like that program is like, good luck. Like you're not getting into that program. Nobody gets into that program. You know? And so what happens is that the women just happen to be applying to programs that were much harder to get into than the men who happen to be applying to programs that are much easier to get into. And so what you could do is, so this is something called, you can look it up if you are interested, but this is something called Simpson's paradox. Contingency tables can help you see how it happens. What you could do is, you could actually systematically discriminate against men in every single program, and as long as all the men piled up in the high acceptance rate programs, at the college level, it'll still look like you're discriminating against women. And it's because as long as the men are in these high acceptance rate programs, your overall acceptance rate for men is going to look good. And as long as the women pile up in the low acceptance rates programs, then your overall women's acceptance rate is going to look bad. But you could actually systematically discriminate at every single level. It's possible. But you wouldn't see that unless you went through a contingency table and looked at these. These are called like conditional or contingent proportions, because that 82% of women, this is percent accepted given that they were women, right? It's sort of a conditional probability, because the overall acceptance rate in that program, that's not the overall acceptance rate in that program. It's just among women. So, anyways, you can look it up. It's called Simpson's paradox. But okay, that's all I got for module whatever we're in, 3. So we will start tomorrow on module 4.
I thought it was interesting too, in like the ones where predominantly men were applying, where
Yes.
we had a higher rate of acceptance, and ones where